Hi everyone, my name's Philipp and I did my master thesis on the manifestly gauge-invariant spectrum of the Minimal Supersymmetric Standard Model. Wow, that's a mouthful, and it sounds quite technical. The idea, on the other hand, is fairly straightforward, and I hope that by the end of this video you will agree that such considerations are indeed important. First up, let's translate the title into plain English so we know what we are dealing with. What about the particles we expect to observe in case some beautiful theory of particle physics is true? That's much better already, and we see that the idea of my thesis was nothing more than to consider a theory and predict particles from it. Okay, but how is this done? Essentially, the theory gives a set of equations and we have to solve these equations to find our particles. As it's often the case with sets of equations though, actually solving them is hard or even impossible. One option we have is trying to tackle them numerically on a powerful computer. But for involved theories, this is not feasible with today's machines. Another approach is to make approximations. And there is sort of a standard recipe that one can follow to arrive at the desired particles. This was, for example, done also for the Standard Model, the most successful theory of particle physics to date. And this is, for example, how the Higgs boson was predicted, which we all know was later found in experiment. Therefore, we can conclude that this approximate recipe is good enough. Right? Well, not quite. Because unfortunately we know that the recipe sometimes fails and predicts the wrong particles. And that would be catastrophic, because if we predict the wrong particles, we will also search for the wrong particles. And searching for something that shouldn't be there in the first place is rarely a good idea. On the other hand, we don't have the computational resources to calculate the particles properly. Luckily, we don't always have to. Very often, we can figure out if the recipe fails or not by applying some tricks, but without doing the costly calculations on a computer. This doesn't give us all the properties of these particles, but at least it tells us whether we can trust the recipe or not, and that is already very valuable. Unfortunately, many physicists don't even know that the recipe can be unreliable. Most proposed extensions of the Standard Model have therefore not been checked for possibly wrong particle predictions. At the same time, many experiments are looking for newly proposed particles. Hence, it is of utmost importance to investigate if they are even looking for the right ones. Which brings me back to my thesis. I considered a very popular extension of the Standard Model, a supersymmetric theory. I found that the recipe in fact does work in this case. That might sound a bit underwhelming, but it's very important. It's a very important result, because it tells us that the experimentalists at CERN, who have been looking for hints for supersymmetry for decades, are actually searching for the right particles. Simultaneously, this is very bad news for advocates of supersymmetry, because the yet undiscovered particles should indeed exist if the theory is true.